Today in the respiratory section, what we're going to focus on is the diffusion of gases. So to start, we're going to start with two basic principles. The first is the concept of diffusion, and the second is the idea that all gases exert pressure, and then we'll describe how this then leads to gas exchange in the lungs in order to get oxygen in and CO2 out of the lungs, and oxygen into muscle and CO2 out of skeletal muscle. So first is this concept of diffusion. The definition of diffusion is that molecules or particles will move from areas of high concentration to low concentration. So we can see here as we insert a dye, the concentration here is very high. All the particles that were contained, we started, if you can visualize each little particle as a dot, they start to expand, filling the space until ultimately each little dot is evenly spaced in the entire area. So again, moving from a low concentration, expanding, having all those molecules then expand into areas of low concentration. In this situation, the low concentration is where there's zero purple dye. As it expands, we ultimately get to where there is essentially a molecular homeostasis, right? So all parts have equal concentrations in them in this very last figure. So that's an idea. We use a liquid here, but the same goes for gases. So our gases kind of reach this homeostasis by diffusing from high concentrations to low concentrations. And then it's also important to note that gases actually can exert pressure. While we may not think about it, what I have here is a balloon, right? The idea of how a balloon stays blown up is when you blow air into it, there are air particles that are, of course, exerting pressure on the outside of the balloon. I should switch colors here. Exerting pressures on the outside of the balloon that are obviously keeping this balloon blown up. Right? So again, when we have a high enough concentration, what we can do is cause pressure. That pressure then pushes out on an object, and that is going to become very important in gas exchange. So first, let's start with the pressure. So gases are commonly referred to as something as partial pressure. I think this is sometimes a misnomer, but the idea is that air pressure is equal to the sum of all of its parts of the pressure that each of them exhibit. Right? This is ultimately explained as Dalton's law. Again, as a definition, is the total pressure of a gas mixture is equal to the sum of each gas that it would exert independently. Right? If we look up the makeup of normal oxygen that we breathe, for the most part, outside of a few trace percentages, it's made up of three parts. One, about 20, a little bit less than 21% of air is oxygen. CO2 is about 0.03, so very low, and the majority of the air that we breathe is about 79%. I mean, if we convert that to a fraction for this next one, so essentially we just move the decimal place 2 places, we can then multiply that by barometric pressure. So this is the average pressure in air. So this is 760 millimeters of mercury here in air. And we can multiply then our fraction times our barometric air pressure. For oxygen, then we get a partial pressure for oxygen of about 159 millimeters of mercury. CO2, about 0.3 of a millimeter of mercury. And again, because of the sheer concentration of nitrogen, about 80% of this 760 gives us 600 millimeters of mercury for a total, if you add all of those up. So what does that tell us? So that tells us essentially the pressure of blowing that balloon up, and in particular when we're interested in these two molecules, right, our oxygen and our CO2, because that's really what is going to drive these gases to and or from the lungs during breathing. One more wonderful physics thing that I know all you students love is the idea of Fick's law of diffusion. So Fick's law says that the rate of gas transfer, or the V for gas, is proportional to the tissue area, the diffusion coefficient of the gas, and the difference in the partial pressure of the gas on the two sides of the tissue and inversely proportional to the thickness, right? So we get, ultimately what we have is this extremely complicated equation. I'll say this, you don't need to know this equation, which I'm sure is a relief for you. Why is that? Is because most of this doesn't change, right? So when we're thinking of oxygen transfer between the lungs and the capillaries, we see that the area of the tissue isn't going to change. The tissue thickness isn't going to change. The diffusion coefficient of the gas is actually a constant, so it isn't going to change. So ultimately, what's going to drive the transfer of gas is ultimately the change in pressure. So going from a change in partial pressure from, in the case of the lungs, from the lungs into the capillaries, right? So this is going to be the primary mechanism responsible for driving gases either out of the lungs or into the lungs, and then vice versa in skeletal muscle. So luckily, the lung is set up very well for this. Again, as we talked about yesterday, the lung has a huge surface area. We'll talk a little bit about that. So therefore, the tissue area here is very large, and the tissue thickness is very thin, right? So if we have a large area and a small thickness, right, this value is going to be very large, which sets the lungs up to be great at transferring gases. So one thing I wanted to hit on just briefly in this lecture is this idea of surface area. We touched on it yesterday in the structure and function of the lungs and talked about that they have this huge surface area. The surface area equal to a tennis court, right? So here's an example of why they have this surface area, and I just wanted to point this out in today's lecture. So if we think of this cube here, the volume is 4 centimeters wide by 4 centimeters since it's a square. Therefore, our volume is equal to 4 times 4 gives us 16 centimeters squared. For the area of a single square, we have 6 faces, gives us a total surface area of 96 centimeters squared in this square here. However, our alveoli, as you remember, aren't set up as one big unit. In fact, they're these tiny little squares to make up a large square, right? And if we think about this, again, as opposed to having 4 centimeters here, each side of the rectangle is 2 centimeters, right? So the area of this square here is 4 centimeters, right? Again, we have 6 faces on a cube, so each cube is 24 centimeters. However, when we make this up, we have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 cubes. Therefore, if we multiply 8 times the 24 cubic centimeters, we get a total volume or a total surface area of 192 centimeters. So again, as you can see, we can take the same size. If you look at this, this is still a 4 by 4 total square, but by breaking it up into these small alveoli, in the case of our lungs, what we do is we increase the surface area drastically from just having one big piece. So I wanted to bring that about to just, again, talk about the lungs. So we have massive surface area equal to a tennis court, thin thickness to set up the lungs up very well for gas transport. And as we know, gas transport from this previous slide, we'll jump back one, is set up very well because large surface area, small thickness, and next will be pressures. So that's what we're going to go into. And what I'm going to do is I'm going to play a video here for you. The video is going to go through the very specific numbers and values of how gas exchange occurs in the lungs and at the tissues, or like for exercise and stuff, but specifically at the muscles. So what we're going to talk about is the partial pressure primarily of oxygen and CO2. We calculated this value earlier. Again, the partial pressure of oxygen in the atmosphere is 159 millimeters of mercury. Once we get it down into the alveoli, our partial pressure of oxygen drops slightly. Our PCO2 is much higher. We'll explain why here in a little bit. PCO2 is 0.3. Right? So as capillaries our red blood cells are coming into the capillaries that surround these alveoli, what we're going to have is gas exchange, right? We have deoxygenated blood, again, coming in, 40 millimeters of mercury, and since our muscles and tissues are creating CO2 in our metabolism, if you'll recall back from breaking down glucose, we get 6 CO2 produced as we break down a single molecule of glucose, then those come in. As they come in, again, we have this gas exchange because our PO2 in our alveoli are 104 to 40. So as you can imagine, this is a large pressure change. Going back to that equation, 104 minus 40 gives us a very large pressure change. So the diffusion of gas is going to happen easily and very rapidly of oxygen to oxygenate blood. PCO2 is 46. That it picked up, and then it releases it into a PCO2 of 40. Okay. We'll note then that in oxygenated blood, it dips slightly, but for all intents and purposes, PO2 in oxygenated blood stays about the same. So we'll note, as it comes out of the lungs, the PO2 is equal to 104, and the PCO2 is equal to 40. So it's equal right as it leaves the capillaries in the lungs, such that the partial pressure of oxygen and CO2 is exactly equal in the capillary and in the blood. Right? We go to the heart. We come to systemic circulation, where our PO2 here is 95, and our PO2 in tissue is typically around 40. Right? So again, we can see that once we get here, we're going to dump a ton of oxygen into the tissues. Right? Our CO2 is the opposite. So we have tissue of CO2 here. So it's 40 minus 46 gives us -6. So we're obviously going to dump CO2 into the blood that then gets taken up. So now what we're going to do is we're going to play a video. This is going to walk you through an animation of this, explain it a little bit better, and again use these same numbers. I'll note that this will be, but I'll end the lecture after that video, but you need to know these specific values at each spot: alveoli, oxygenated blood, and tissue and deoxygenated blood. You need to know these for quizzes and exams.
Fresh air entering the lung carries oxygen with a PO2 of 160. The presence of moisture in the lung results in reduction of the PO2 to 104. Fresh air entering the lung carries carbon dioxide with a PCO2 of 0.3. The carbon dioxide delivered to the lung from the blood raises the PCO2 to 40. At the arterial ends of the pulmonary capillaries, oxygen diffuses from the air in the alveoli into the blood, and carbon dioxide diffuses from the blood into the alveoli because of differences in partial pressures. As a result of diffusion, at the venous ends of the pulmonary capillaries, the PO2 in the blood is equal to the PO2 in the alveoli, and the PCO2 in the blood is equal to the PCO2 in the alveoli. With no differences in partial pressure, there is no more net movement of oxygen or carbon dioxide. Oxygen diffuses out of the arterial ends of tissue capillaries into the tissue fluid, then into the cells, and carbon dioxide diffuses out of the cells into the tissue fluid, then into the blood because of differences in partial pressures. At the venous ends of tissue capillaries, the PO2 in the blood is equal to the PO2 in the tissue fluid, and the PCO2 in the blood is equal to the PCO2 in the tissue fluid, resulting in no more net movement of oxygen or carbon dioxide. The blood now carries the oxygen and carbon dioxide to the lungs. In the body, all of these exchanges occur simultaneously.